Hi everyone, hope you are doing fine. So again today I am going to solve the LeetCode daily challenge problem, and after that I am going to solve the uh, weekly contest 503. So yeah, let's start with the daily challenge problem. So the today daily challenge problem is network recovery pathways. So in this problem we have given us like a directed acyclic graph of n nodes numbered from 0 to n minus 1, and this is represented by a 2D array. Like we have given something like edges array with UOI, VI and a cost I, indicates there is a one-way connection. Like there is a one-way connection from node UI to node VI with the recovery cost of I. So yeah, some nodes may be offline. So you are also given a boolean array online, where online of I equal to true means node I is online, and node 0 means like if the online I value is equal to true, it means that the node is online, as it means that if it is false, it means that node is offline. Like node 0 and node n minus 1 are always online. So we have to find a path from a 0 to n minus 1 is valid if all intermediate nodes on the path are online, and the total recovery cost of all edges on the path does not exceed k. And the total recovery cost of all the edges on the path does not exceed k. So yeah, for each valid path, define a score as the minimum edge cost along that path. So return the maximum path score, that is the largest a minimum edge cost among all the valid paths. If no valid path exists, return minus 1. So what we have given us something like a 2D array where we have given UI, VI and the cost I. Where UI and a VI, there is a edge between node UI to VI, and this is a one way, like a directed acyclic graph. So this is a one way edge. And we have then given an online array where the value equal to true means that that node is like online, and else if it is false, it means the node is offline. And we also have a given a value of k, and like a total recovery cost of all the edges on the path does not exceed k. And after that, by this it means, I think they mean that, like 0 to 1, in this case all our node are active. Let's take this example, in case node 4 is not active. So we firstly go from node 1 to node 4. Then we can't go from node 4 to any node. So yeah, so the cost reached to node 4 is if we reach from 0 to 1 in cost 7, and 0 to 1 to 4 in cost 2. But 2 is false, like that is it means that the node is offline. Like you can see that cost is 7 plus 5 equal to 12, which is less than equal to k. So the path is valid. Yeah, total cost is, and the minimum edge cost along the path is 5. And we have something like another there is a path from 0 to 2 3 4, and the node 3 is offline, so this path is invalid regardless of the cost. So yeah, so from the problem, it means that they if the node is offline, we can't go through that node. So yeah, so after that, excluding that part, so we have to return like a best possible way to reach that node. So yeah, you can see it's something like a shortest path from node. We have to find the shortest path from node A to node B. But the main catch is that we have to track like this value. Like for each valid path, we have to track that the score must be less than k, but also like we have to maximize that a minimum edge cost. In this case, like if we go from 0 0 1 4. So the cost is going to be a 5 because the minimum minimum cost edge is 5. That is the minimum for all the edges. And if we go from 0 to 2 and from 2 to 6, the minimum edge cost is 6. So I think in this case the output is going to be a 6. Yeah, you can see. So that's in this problem. So yeah, so let's see how we can solve this problem. So let me copy this and open my, and let me arrange the screens. Yeah, and let me copy this input also. So yeah, so we have like a graph like this. You can see like there is a edge from 0 to 1 and the weight is 7, and another edge is from 1 to 4, like there is a edge from 1 to 4 and the cost is 5. And then again we have something like edge from 0 to 2 and the cost is 6, and again there is a edge from 2 to 3 with cost 6, and 3 to 4 with cost 2, and then last one is from 2 to 4 with cost 6. And so like a node 1 is online, I am writing here 1 here, and node 4 is online, like node 4 is online, node 3 is offline. So I am writing like, let me write again here 0, and node 2 is online and node 0 is online. So like we have to maximize the minimum, like maximize, so in this case maxi, but I am writing so I have to maximize the minimum cost between, we can say edge, between, like we can say between nodes, between two, between nodes in a path. So we have to maximize the minimum cost between nodes, minimum cost between nodes in a path, like we have to move from, like in this case we have to move from 0 to last node, that is a 4. So yeah, if we move from 0 to 4, let's say first approach is like we will try to find all the paths. So yeah, like 0 to 1, first one is 0 to 1, and then from 1 to 4, and the cost is going to be a 7 and a 5. So another path is like something like 0 to 2, and then from 2 to 4, and the cost is like 6 in both cases. And another path is like something like 0 to 2, and then from 2 to 3, and from 3 to 4. But like this path is not valid because the node value 3 is false. So we by false I mean that the node is offline, so we can't go through a offline node. So yeah, let's see now how we can like, so first approach is like we can generate all the possible path. So but like if we are going to generate all the possible path, then it is going to be a like exponent, like time complexity of this is going to be exponential. So yeah, so let's try to find a better way to solve this problem. So let's say if we have something like if we don't have to maximize this thing, and we have to check for like k equal to like k equal to 6, whether this is possible or not, like sorry yeah, so we have to check like our maximum value can be up to k, like sorry, maximum, not maximum but a minimum value, like minimum value that we can choose is up to k. So yeah, so if we traverse from 0, we have two options from let me erase this thing. So if like, so if we go like, if we at 0, from 0 we have two options, like we can either go to 2 and either go to 1. So if we go to 2, our cost is like a 6, and a k like a cost is 7. So instead of k, it is going to be a cost, like we can take up to that cost, like like we need minimum that much cost, like we can't take minimum that than this. Then from 2, then from let's say 1. Now let's say, like, because 1 is the maximum thing, let's say we take this thing. So from 1 we can go to either, yeah, we can only go to 4, but from 1 to 4 the cost is 5. But we are checking it for 6, so we can't take minimum than 6, so we can't explore this path and return from this. So yeah, now another option we have left is like a 2. So from 2 we can go to 3, and another is like we can go from 4. So yeah, for both cases the value is 6, and our cost is also 6, so yeah, we can take this path. So let's say we take this 4 path. Yeah, but now 4, in case of 4 we reach our like nth node. So yeah, it means that there exists a path. So what is the minimum value in this case? Like minimum value for this is like is 6, because we are taking, like we can take minimum, like minimum of cost which we are choosing. So we can say that there may be possibility that a 6 can be answer, but we are not sure. But we guarantee that 6 can't be answer. So you can see like this is something like whenever we have to do something like maximize the minimum or minimize the maximum, so we can think of something like a binary search. And you can see like another thing is like if we have to something like, if the we have range from 1 to n, and we can say that for any k, if this is possible, for the k is possible, either the left part left part answer is true, either the right part answer is true. In that case we can use binary search, because in that case like if the we can say that for left it is always going to be true, then we can eliminate the left part. So the main reason, so the main idea behind binary search is that we are going to eliminate the half part. So in this case we are going to eliminate the half part. So yeah, binary search is good to go for this case. So yeah, so but now we have to find this thing in an optimal way, how we can do this thing. So like this is similar to the problem we solved yesterday, I think. Yeah, yesterday and day before yesterday. So like I think these three problems are correlated with each other. So let's see how we can do, let's say write a pseudocode for this thing, how we are going to achieve this thing. So let's see, we can uh, yeah. So like this is a standard problem, how to do something like this, to traverse from 0 to n node with the some k cost. Like for every value we have, the cost must be less, greater than or equal to k. So we are going to take a priority queue of like a max priority queue, max priority queue be of like a pair of, we you can also take a array, like array also, like a pair of we uh, instead of doing writing something like this, I can write something like this. uh it is going to be something like int comma int int. Yeah, so this is going to be like the cost. Yeah, this is going to be a cost, and this is going to be a, like, we can say, node value. So like in this case, I think we don't need to store the cost, extra cost. So yeah, pair of pair will also work. So I think there is no need for this thing. So we can use only pair of int comma int. So first one is the cost, and second one is the node value. Then so first initially we are going to add something like, what is the cost? So cost to reach one is, we can say, we can add something like infinity value, which is going to be a very large value, and with node value 0. So now so we will check from 0 where we can go. From 0 we can go to like something like 1 and something like 2. So yeah, so we check like if the cost reach to 1 is less than equal to the cost which for the cost which we are checking, like the cost which we are checking, let's say we are checking for 6. So we will check if it is sorry, less than, not greater than, it should be greater than k, greater than equal to cost. So if it is greater than equal to cost, then we can take this path. In this case it is 7, and in this case from 0 to it is 6. So yeah, we can take both this thing. So now after that we are going to add this thing in queue, cost 7 and the node value 1. So initially our queue has something like this. Then we are going to like pop this out, and we'll add queue, our queue look something like 7 comma 1 and 2 comma 6. Yeah, now we again pop the maximum thing, so it will be popped out. And from 7 1 where we can go, like cost 7 and the node 1. From node 1 we can go to either yeah, we can only go to 4, but you can see the cost here is the 5. So cost is 5 to reach the node 4. So we can't, we will not add this thing to our queue, because we are taking the cost as 6. So we want the cost reach from reach to node u to v must be greater than equal to that the cost which we are checking for. So we will skip this thing, and again we will try to pop out another element. Then like in this case it is 2 6. So from 2 we can go to like 4, and the cost is also something like we can say it is going to be like 6 comma 2, and the cost is 6, and we reach node 4. So yeah, we, and also this node is a last node, like n minus 1 node. So in that case we may return our answer. But like we are going to update this with the minimum value, like if our like this whole graph looks something like this. This value is 10 and this is 16, this is going to be 6, and this is like something like 8. Or we can say this is going to be 8. Firstly this is 8 and this is 18. So yeah, so in this case from 0 to 1 the cost is going to be something like 18. So we have something like 18 comma 1. Oh sorry, it is 8. So it is going to be 8 comma 1. Then whenever we move from 1 to 4, we will not something like 18 comma 4, because we have to take the minimum. So we are going to take overall minimum, like minimum of this, the node which we are checking, from node which we, from where we are moving, like us yeah, like ui value to vi value, like what is the minimum cost to reach ui and the minimum cost to reach vi, like minimum of both the case. So yeah, that's it for this problem. And then we can do like uh do binary search simply, like from a range from like we can say 0 to infinity, and infinity is like we can say like 1 is 6, or we can write it as 1 is 9. So yeah, uh so in this case the like to achieve this thing, the time complex like to do this thing, the time complexity is going to be a something like what is going to be time complexity. We are adding n node, and the time and the priority queue time complexity, like and log n for this and log n for this. So yeah, log n for binary search. So it is going to be a something like n log square n, and our constraint are I think 10 raised to power 6. So it is going to be easily pass this thing. So yeah, let's write the code for this. So yeah, what like constraint are up to 10 raised to power 4, not 6. So yeah, let's write the code for this. So we have some, let's skip this part taking input, and we will directly run in a lead code. And yeah, so we have something like we have given edges. So firstly we have to convert this edges to adjacency list, and size of adjacency list is going to be a edges dot size, like yeah, vector of pair of, like we need a vector pair of pair. Yeah, now we will try to iterate the edges and do something like adj of it comma 0 dot push back. We are going to add the it of like 1 and it of 2. So it means that from if we are at uh, node like it of 0, we can move to node it of 1 with the cost of it of 2. Yeah, so that's it. Now our adjacency list is ready. Now we need priority queue. Our priority queue is going to be a like max priority queue of pair of int comma int pq, and we are going to add something like pq dot push, pq dot push. Firstly we have something like, we can say infinity con infinity is going to be a 1 is 6, or we can say 1 is 8. Let's take a large value, and we are going to be yeah. So value is going to be infinity, and the node is going to be a 0, and we will try to iterate until our priority queue become empty. Also I think I skipped the one thing. So like there may be a possibility like something like this. We can say we have something like our tree might look something like this. So there may be possibility like if it has value 8 and it has value something like we can say 7. So yeah, there may be possibility like we can reach here earlier with minimum value of 6, and but again we can reach here from 7. So I think like this case is not possible, will not possible, or is it possible? Like if we have something like 10 here, not 10, we have something like yeah 10 here, then 6 here, and yeah, if we reach that 10 is going to be, firstly we insert 10 because it's maximum, we will take 10 and then add 6 like this thing in our priority queue. Then this 8 will run, this 7 will run, and then 6 will run. So yeah, this in this question this will be handled automatically because we are going to take the maximum only in a queue firstly. So yeah, let's keep this thing and write the code. So we are going to take the it equal to pq dot top, and we are going to pop this thing, and like and cost is going to be a it dot first, and in like we can say node is going to be a it dot second. So now we can iterate from iterate to its urgency node. So it is going to be like urgency of so we can say iterator equal to like urgency of node, and like in this case the new node is going to be like from like we can say vi node is going to be a itt dot first, and in new cost is going to be a itt dot second. So yeah, so we can check if the, so as we have to do this thing for like multiple like we have to apply binary search on this, so instead of doing this here we can do it in a function. So yeah, let's say yeah. So we need something like vector int adjacency list and a vector bool online and comma like we need a long k like yeah k value. So so we have to also maintain the cost, so I think we have to add this thing also, so we can all, so we can also maintain this k. So for that I think we need to take a pair of pair of pair only. So yeah, it is going to be a pair of pair, and it is going to be something like first value is going to be a cost, second is going to be a node value, third is going to be a total like total cost to reach that node. So yeah, I think we can simply take this here from here to here, and it is going to be infinity comma 0 comma, and the total cost will initially be a 0, and we can also make this all value as long. So yeah, so now long we can say total cost is going to be it dot second dot second, and node value is going to be a first, and we can say like yeah. So now we can check if the total, so as we have to maintain the total cost, we also need to maintain the value of that total cost also, because if we need something like a better like we again reach, there may be possibility that with lesser cost uh, we get some like a better total cost, because less total cost. So in that case we can take that value and try to find our answer. So yeah, we can declare it is a int max. So and for like a dp of 0, it is going to be a I think a 0. So if the like what is going to be overall total cost, new total cost is going to be a total cost plus new cost, and if the new, we can simply if the new total cost is less than or equal to k, we can take this thing, and also dp of new node value must be like new total cost must be less than new total cost must be less than this value. In that case, we can simply take that. And also we have to check another firstly we check like it the cost must be less than k and the new total cost must be less than k. Yeah, like I think these are the two conditions we have to check. If this is a true, then we are going to like dp of new node value is going to be a new total cost, and then we can simply add pq dot push. So firstly we have to push the minimum value. So minimum value is going to be a like int new min cost. New min cost is going to be a min of we can say new node, sorry, new new cost, comma we can say like something like what is the second value, we can say cost, something like cost, and we can simply add here the new min cost, comma like the node value, node value is like new node, and the total cost, new total cost. Yeah, I think yeah this is done. And we can also check like if at anybody any time we our node is going to be a n minus 1, it means that we reach, and we can simply return true. And if our loop will completely run and we don't get any answer, it means that it is not possible in this for this k value like k value. Yeah, sorry, new total k value, new total cost must be less greater than or equal to k. So yeah, I think it's done now. So let's write simply check function initially our low is going to be a 0, I can say, and high is going to be a, I can write something like 1 is 8, like infinity on infinity, and while low is less than equal to high, int mid equal to low plus low plus high minus low divide by 2. And like if the mid value if for the mid value this the answer is true, so we have to firstly pass the adjacency list, and then we have something like online. So I think we have skipped the online thing, online, and another thing is like a mid. If for this mid value is true, then low is going to be a mid plus 1, else high is going to be a like mid minus 1. So at the end we can simply return the high value. So also we have to check like what we have to check like online value of this new node must be a true. So yeah, these are the thing we have to check in this case. So yeah, I think let's try to run this uh, using ll, like, or we can say we can simply copy this thing. Let's try to run this thing. I forget to define the data type for this so yeah, why we are getting, so we also need to pass here the n value, and n so we can simply pass n. So it is going to be a something like this. Again, we are getting itt dot first. Yeah, let's define it as ll. No, I think there is problem in something else. Yeah, I think it is going to be a pair of int comma int, because we are taking a pair of int in a, like, you can see here, not here. Ah, adjacency of and plus one, we can say. We can make all the value as a long. So yeah, we are getting the output, but we are getting the wrong output. So let's see the second example only, because we have checked for we have dry run that problem also. So yeah, let's see why it is not giving us answer, and let's try to like make this infinity value as 12 only. So if we make this 12, so mid is going to be a 6, so we can check for mid equal to 6. Why it is not giving a correct answer? Mid is going to be a k in this. Yeah. So yeah, let's see, is it working or not. So yeah, firstly the mid becomes 6, and for 6 it give us a wrong answer. So from 6, what all the value where we can go? And new total cost must be less than, and the new total cost must be greater than equal to k. Sorry, this is going to be a k, k, and also we need something like actual, like we can mark this as a k, and we can take simply mid again. Now instead of k we have to check for this must be greater than equal to mid, and also our value must be like, we have to pass something like k here also. Yeah, so it is going to be like new total cost must be greater than equal to mid, like new total cost must be less than or equal to k, and something we can say new mean cost must be greater than or equal to, we can say, mid. So yeah, let's try to run this thing. So we get true for first, but we get false for second. So why low plus high minus low? Low is going to be a 0. Yeah, mid become 12. Then why it is mid, it show mid as something like 12 only. So we are printing here k. So it is going to be a mid is going to become 12. Yeah, but for mid we are not getting our answer. I think we write something wrong here, like new total cost must be, I think, new total cost must be less than equal to k, and the new min cost must be greater than or equal to mid. So let's see the what is the node value. New node, we can say a new node, and new min cost, new min, uh you can say new min cost, yeah, and total, we can something like total, and new total cost. So let's try to run this now. So from 0 we go move to 1 with new min cost of 7 and a total of 7. And then also from like sorry 0 we can move to 2 with cost 6 and a total of 6. Yeah, then we reach to node 4 with min cost of 5. So yeah, I think for 6 we are getting true value because we reached like we can say something like, yeah, new mean cost is greater than equal to mid. This condition is true. And online of new node like 4 is, we can say 0, 1, 2, 3, 4 is true also. This condition is also true. So we can simply write something like yes. So if we see yes after that, it means that it is added to our answer. So yeah, new node is going to be a, yeah, I like it dot second dot first, yeah, it's correct. So like this, in this case it is not working, so but I think it should work. Like you can see like, yeah, but it is working. New node 4, cost is 6 and the total is 12. What is the value of n? 3, 4, 5, 6. So sorry, so n is going to be a online dot size, I think. Online dot size. So I think it should give us correct answer now. So yeah, so let's try to summarize this. I think today it should work because yeah, I think our solution is optimal, and let's output 12 and expected 39. Why it is giving us a 12? There is no value of 12. Oh sorry. So I think we have to make this as a like infinity because it is not checking for the value greater than 12. So yeah, let's see now. Now everything is LL. Yeah, I think the value can be up to like k value can be up to I think like 10 raised to power 9. But yeah, I think for 10 raised to power 9 it should work properly. What is the value of k? I am taking it as now long. Low is this, high is this. So yeah, let's print here mid. Verify like for what values it is checking. Again, it is not working. Yeah, it is checking, I think, but it is giving wrong answer for everything. Uh, so, oof, we are pushing all the edges. Mm, there is only a directed edge, a one-way edge, UI to VI, and then low is going to be 0, high is going this, mid is going to low plus, high minus low divided by 2. And if this is condition is true, adjacency online k mid and low equal to mid plus 1 and high is equal to mid minus 1. So yeah, we are going taking a priority queue. uh so yeah, so it is going to be a long I think, or we can say it is as 1e16. I think now it should work. I think so. Why it is in why it is not working? So yeah, now it's give us answer, but again it is giving a wrong. Where we use int, like this is k is ll, mid is ll, and n cannot be in a like long. So yeah, urgency online is going to be true, like 33678. Long max we can say. So expected is like 10 raised to power 9 and we are getting 10 raised to power 8. So how is it possible? So are we checking condition in a proper way? Like online of new node must be true and the new total cost like total cost plus new cost must be in a must be less than equal to k. Yeah, new total cost must be less than equal to k. And new total cost must be less than dp of new node also. So we can also like write something like skip this if the total cost of total cost is less than dp of, we can say new total cost node, it must be like we can skip that, skip in this case. So where are you using infinity? So yeah, so it is going to be a, we can say 1 is 16. 1 is 16. Let's try to run now. So yeah, because like we are entering here the like lower value and the answer can be great, answer was greater than that value, so that's why we are getting this wrong answer. And for now TLE we can like, as we use log anywhere, I don't think we have used something log, lots of log anywhere. Then I think it should work. So we can simply check if the online of either the IT of 0 equal false, or online of IT of 1 is going to be false, then we can simply skip this thing. So let's see. Can we do something like this? I think it's passed by reference only. If we do something like this, yeah, or we can simply declare this in a global. So let's say we declare it is in a global, and then can be up to, like, we can say 1e, not, we can say 1e5, and we can remove this thing from here. Also from here, and now try to run this thing. Again we are getting TLE. Let's see for how many iteration it is working. It is going to be something like this. Let's see how we can solve this, like binary search answer and check if the particular answer is possible including all the edges. Wait, yeah, we are using same approach. Implement the check function using either discasters or dp via topological sort, since it's a DAG. So we are using something like, we can say, discasters algorithm only. So we are updating the dp value also with the new total cost. So how we can further optimize this thing, like So instead of doing something like this, let's write it in here only. Vector pair of int comma int adjacency list, and we can simply pass adjacency list here also. I think one optimization we can do something like this can always be going to be a int, and also this is going to be a int, and only this value is going to be a long, because it's also take like 8 byte in like in case of yeah, but where we are getting outside the range of int, where because this value is not going to be a greater than int. Yeah, so we can do something like int min also here, sorry, int max. Here we are getting like this is going to be a, I think the mid value, and mid can be a less than equal to, we can say we can do something like -1, let's say. New min cost and new node also, like how new min cost is new min cost is min of all these things, and this cost values can be up to 10 raised to power 9, and k can be up to 10 raised to power 13. Where is k? K is here, k, and we can make this as int also. Sorry. So yeah, this can be, I think, int max. This can be up to int max only. I think again it is going to give us TLE. Yeah. We can further optimize this thing. Like we are checking if the total cost is less than if the total cost is less than the current cost, then there is no benefit of taking that thing. Yeah, that's true. In that case we are simply continuing, but if the node is already is, and then no need to continue. So let's see, I have already solved the problem. So uh like how I do that time. So yeah, I solve it in 2025. So let's see. Yeah, same approach. But in this case, I am taking the minimum thing first. Uh, the minimum is going to benefit us. So yeah, yeah. So instead of taking the maximum, like we have to take this as a minimum thing, PII, and like a greater of PII. So this is going to become PI, and we can define it as using PII equal to this thing. So let's try it now. So it is 3 times I. Again, I am getting TLE. So what is the benefit of doing this? So yeah, I think it's a pretty similar code. Yeah, this optimization I have already done. Same thing doing. Uh, same thing. But instead of doing like true false, I am returning the cost here. If the cost is less than equal to k, then I am simply making low as mid plus 1, else high is going to be a mid minus 1. So I think in this I am not maintaining the total. Like we also have to maintain the total recovery cost of all edges must not exceed k. How I am checking that? Oh, so I am checking by this way. So I am finding the shortest path. So yeah, so I think we can do something like that. Like I am trying to generate all the path and then do something like that. Like try to path all the path with the minimum like. So instead of doing, we can simply use die clusters to find the shortest distance between two node. So in that case, we will skip this thing like. So yeah, so we can simply return some value from here, and we have to also do. So it will look something like we have something like priority queue of PII comma vector of PII. We can say, yeah, greater comma PII. So now it's going to be standard Dascastras algorithm. We have to add start comma 0 and LL. Total cost is going to be initially 0, and while not of priority queue become empty, we have to simply LL cost is equal to PQ dot top dot first, and LL node equal to PQ dot top dot second, PQ dot pop. So if node is equal to n, then we have to return DP of a node, the total cost for that. And else if like yeah, if the cost is greater than DP of node, then also we can simply continue, because we have already find something better than this. Else we will try to iterate that node, and if the it dot second is greater than equal to like max cost. By max cost we mean that mid. If it is greater than equal to mid, it means that we can simply take that thing, and temporary cost equal to cost plus it dot second, we can say. Yeah, if temp cost is less than like a DP of it dot first value, then we are going to replace that it dot first value with the temp cost, and PQ dot push temp cost from it dot first, we can say. And last we can simply return the total, like return DP of, and what is the minimum to reach this DP of and. So we have also do something like here LL temporary answer is going to be this, and if the temporary answer is greater than equal to, sorry, it must be less than equal to k. Yeah, I think. So what, like I am. So yeah, let's try to submit it now and let's see if it is working or not. Yeah, now it's working, and now let's try again to dry run and understand this code in detail. So we can simply go here, ray.so, and remove background and export this image. We can simply copy and simply paste here. So yeah, let's start here. So firstly, we are what we are doing. We are simply taking this, creating this urgency list and making this urgency list. And if the like both the value are offline, we are not like if one of the values offline, we are not going to that. Like we can say that as in that node in our adjacency list, and then we are simply doing a binary search, and in binary search we are finding the shortest path, like, so we are fixing the so let's take our example, like if we have something like yeah, we have something like this. Yeah, so if we have something like this, we are trying to fix something like we can say the every here has something like cost 6 6 5 and 3. So sorry, we can make it as 13. So yeah, so first we are fixing the value of the cost, like for this we can only take the value up to this cost. And so now if the values, let's say if the value is 5, so we can take up to 5 thing. So let's take this 7, we can take this 7 also, the 5 also, so we have something like this path. But we are calculating the what is the total sum of that path also. So firstly we are finding try to find the shortest path with this condition, that is cost must be less than equal to 5, less than equal to, yeah, that's mid. So for that, we are taking a priority queue, and the priority queue has something like the cost and the node, cost and the node. So initially the cost is going to be a 0, 0, and the node is also going to be 0. Then we are making this priority queue as a min priority queue because we have to take the minimum cost thing firstly. So yeah, so we are taking the first is the minimum cost, and the second is the node value, and then we are popping out that node. And if the node value is going to be a minus, like node is the last node, it means that we have reached, so we are going to return the dp of node value, like what is the minimum cost to, like minimum cost to reach that node. So it's a simple discusses algorithm, and this is optimization, like if we have already processed the cost which is greater than this cost, then we can skip that case, and as we are iterating to its, like if we have something like that tree node, we are iterating to its child, and we are checking like if the cost to, like if the cost to reach this must be greater than equal to mid. Yeah, that's we are checking, like we are fixing the 5, the cost must like reaching to this node must be greater than equal to 5. If it is greater than equal to 5, then we will check like what is the total cost. And if the total cost is going to be like the previous cost plus the like second it dot second, that is the cost to reach from this node to this node. Yeah, so like if this value is less than if the new value is less than to reach this node, then we are updating that value and pushing the same value in the queue also, so we can again process this thing. And we are marking this dp, like dp in, we can say with the max value, like a very huge value, that is not possible. So yeah, so that's it for this problem. So yeah, so I think that time is like now around 3:15 a.m. So yeah, so far today we can uh, we are going to skip that like contest problems. So yeah, so today is Saturday, so I will going to start like uh in the evening only. So if I start like in the evening, so I'm thinking of going live and solving the problem live, and also thinking to solve like a tree or DP problem set of CSC also tomorrow, like today only. So yeah, that's it for the video. So thanks for watching this video.